Hello everyone, my name is Dong Yong and my matrix number is CE190137. First of all, I would like to express my sincere gratitude and special thanks to Dr. Jais Invias give me this opportunity to present about the project title Fabricate the zinc oxide bilayer by using the sputtering method, which are related to the course BEJ43603 Material Characterization. We are from Group 4 and from Session 1 student. Today, I would like to present about the introductions. There are various methods to deposit the zinc oxide thin film, but most common method is sputtering method. The sputtering is a process that involves the bombarding target material, in the case zinc oxide, with energetic ions such as argon in a vacuum chamber. This causes the atom from the target material to be ejected and deposited onto a substrate, such as the glass or silicon, to form a thin film. The process relies on collision between the particles and the electrons, and also the momentum exchange the result. Therefore, a voltage is applied between the target materials and the substrate, which causes the electron to be accelerated away from the targets and collide with the atoms of an inner gas, such as the argon, which is present between the cathode and anode. The collisions ionize the base atom and accelerate them into the target material. When this ion collide with the targets, energy is transferred from the ion to the target atoms, and if the energy is sufficient, an atom is ejected and deposited onto the substrate. Next, sputtering is the higher rate deposition technique that does not produce toxic gas. It is easy to scale up for large glass substrate and is cost-effective and simple. It is widely considered one of the best methods for depositing the thin films due to its efficiency, scalability, and film uniformity. The zinc oxide is a widely used semiconductor due to its unique properties such as the stability, transparency, and wide bandgap. It is commonly used in various applications such as the solar cell, liquid crystal display, light-emitting diodes, and thin film transistor. The RF magnetic sputtering method has been used to fabricate a zinc oxide thin film to produce the high-quality thin film. This study has also been conducted to investigate the morphological, structural, and electrical properties of the zinc oxide thin film. For the structural properties, the X-ray diffraction can be used to determine the crystal structures and crystal quality of the zinc oxide thin film. The X-ray diffraction pattern can reveal the information about the preferred crystal orientation, crystalline size, and presence of any defects of impurities in the film. For the second one is the morphological properties. Two of the tools is used to investigate the morphological properties, such as the atomic force microscopy and also the scanning electron microscopy. The atomic force microscopy can be used to study the surface morphology and roughness of the film. The atomic force microscopy image can provide information about the size, shape, and distributions of the particles on the surface of the film, while the scanning electron microscopy can also be used to study the morphology of the films. It is an image that can provide information about size, shape, and distributions of the particle on the surface of the film, as well as any defects or impurities that may be present. For the third one is the electrical properties. The electrical conductivity of the film can be measured by using the 4-point probe and Hall effect measurement. This measurement can provide information about the carrier concentrations and mobility of the films, which can be used to determine the electrical properties of the thin film.
Next part is the literature review. According to the research papers, that the analysis was performed to determine the structural properties of the prepared zinc oxide thin film. It was found that the diffraction pattern obtained for coating deposit at the metallic mode revealed the coefficient of metallic and oxide hexagon phase of zinc and zinc oxide. Furthermore, the zinc oxide coating deposit at working point and had the photocrystalline structure of the hexagon zinc oxide phase, with the most dominant peak occurred at 2 theta, which is equal to 34 degrees. And the associate with the 002 lattice plane, the lattice plane observed for the zinc oxide film deposit in the depth dielectric mode were more intense than for the film deposit in the shallow dielectric mode. The growth rate of each crystallographic plane differ based on the crystal orientation and surface energy. Alright, next, the surface morphology of thin film was observed using a field emission scanning electron microscope at room temperature. The surface morphology of zinc oxide thin film grow at low substrate temperature at 335 degrees Celsius shows small crystallinity with the high intensity. By increasing the temperature to 535 degrees Celsius, the crystallinity of the thin film was enhanced, and we obtained a large crystallinity. The morphology of gross zinc oxide with different thickness of argon nanoparticle coating is despite. Energy dispersive X-ray was implemented in different areas of the sample, which confirmed the chemical composition of the zinc oxide. The researchers state that the current voltage characteristic measured in the planar configuration. Zinc oxide film show very high shear resistance with nanostoichiometric zinc oxide film has low shear resistance. The electrical characteristic of zinc oxide thin film was mainly dominated by the electron, which are generated from zinc intensitation atom and oxygen frequency. As in many other semiconductors, the conductivity of zinc oxide increased with increasing the temperature.
Assalamualaikum, my name is Muhammad bin Shafiq. I will present about methodology, equipment and process for the deposition of sand. zinc oxide, thin film reactive pulse magnetron sputtering process of metallic zinc target was used. Deposition process were carried out in an NP500 vacuum stand setup for Leslavik, Poland, equipped with a pumping system consisting of diffusion and rotary pumps. The final pressure obtained with a vacuum set was equal to 2 times 10 power of 5 negative 5 torque. Its sputtering process was carried out in the atmosphere containing a mixture of argon and oxygen gases, and the working pressure of the gas atmosphere was changed in the range from 1 times 10 power of negative 3 to 8 times 10 negative 3 torque. Circular magnetron handmade was used, which was equipped with a high purity circular zinc 99.999% disc with a diameter of 100 mm and a thickness of 9 mm. The used magnetron offered the possibility of conducting processes with a very high power release in the sputtered target, which is directly related to the efficiency of the deposition processes of thin film. The magnetron was powered with using a MSS 10 kW power supply unit. A distinctive feature for this power supply unit is the possibility of in-sight observation of sputtering processes by monitoring its parameter. In particular, the most important parameter is called the circulating power, the term introduced by the Dora power system, reflecting changes in a low impedance. In turn, impedance is determined by specific technological condition in the sputtering process and is affected. Thin film were deposited on fused silica, silicon, and aluminum substrates containing interdigit electrode designed for electrical measurement. The thickness of the deposit zinc oxide thin film was assessed with the use of the Taylor-Hobson CCI light optical profilometer. The microstructure was studied by X-ray refraction in grazing incident method using a panel-optical expert diffractometer equipped with a copper KUKA X-ray source with a wavelength of 1.5406. Crystallite size analysis was processed according to the Debye-Sherrill equation with the aid of MDI Jet 5.0 software. Optical measurements were conducted in the wavelength length of 300 until 1000 nanometer using an Ocean Optic QE65000 spectral photometer and couple of deuterium halogen light source. The measurement of transparent zinc oxide thin film were completed by evaluating the fundamental absorption edge, the refractive index, which is N, and extinction coefficient K. Spectral characteristic of the transparent film were determined by the reverse engineering method using the FTG FilmStar software. Employing a generalized Cauchy model for material with K larger than 0. The resistivity of the deposit coating was determined using current voltage characteristic measured at room temperature in a duction enclosure with the aid of a Catley SCF4200 system and an M100 cascade microtech probe station. The mechanical properties of prepared zinc oxide thin film were determined using nano indentation method with the aid of CSM instrument. Nano indenter equipped with a diamond picker stick. The result were analyzed using the method proposed by Oliver and Farb. In turn, this scratch resistance of the deposited zinc oxide thin film was measured using the Bayer test and the table of selective aberration tester 6160. The oscillator movement of the abrasive medium, that is 6/9 silica sand, simulate the everyday wear of the measured coating. The resistance to abrasion was determined using the oscillating sand test described in STM F735. The movement distance of the sand tray was equal to 100 mm at a speed of 300 strokes per minute. The surface topography of the deposited thin film was examined before and after the scratch test using Telesurf CCI light Taylor-Hobson optical profiler and an Olympus BX51 optical microscope. As an indicator of scratch resistance, a comparison was made of the mean square root height square measured before and after the abrasion test in equation 1 as well as equal to SQ before over SQ after times 100%, where SQ before is the mean square root height before abrasion test and SQ after is the mean square root height after abrasion test. It can be estimated that the closer the SRS is to 100%, the more resistant the coating is to crashing due to negligible change in the roughness of its surface.
So now I'm going to talk about the result for the first characterization, which is morphological. For the direct sputtering deposition from a ZNO target with DC power, the surface morphological shows that with a low AR working pressure, the surface of the pillar was not flat, showing the formation of oxide island among smaller cluster. As the number of oxide island decreased, with increasing pressure, the size of the cluster increased. So we can see from the figure 1 here. So next for the structural. So here is the X-ray diffraction spectra of magnetron sputtered ZNO thin film. So all film exhibited 002 preferential orientation with clear peak, shape, and high intensity. And AL doping decreased the intensity of 002 to a certain degree. With reactive magnetron sputtering using RF, it was observed that the negative bias applied had certain influence on the uniformity and compactness of the film. The film with a bias of negative 50 V was more uniform than the other two. So next for the electrical. Firstly, the ZNO thin film with good conductivity showed that the 002 disk space is close to the of the standard power sample, while film with poor conductivity has large disk space value. It was revealed that the disk space and log P has a good linear relationship, which is shown in the figure 3. So for the secondly, almost all film prepared by DC sputtering from the ZN or ZNO target have high resistivity, while the thin film with RF sputtering have low resistivity to the level of 10 to 3 cm. Then thirdly, SAM observation suggests that the conductivity of the film may be affected by the microstructure from the cross-sectional micrograph. It can be seen that the oxide grain in the DC film grow mainly along the C-axis to form a good columnar structure, while the RF film grow also along the C-axis, but the grain grew with less columnar structure and much diverse orientation. The surface morphological show that the RF film have denser feature, smaller gaps between cluster than the DC film. Dense microstructure with diverse growth and direction seems helpful to electron conduction. So lastly, for the conclusion, direct sputtering deposition from outside target was highly influenced by the pressure level in the working chamber. A high pressure produced film with smooth and regular morphological feature, where this sputtering deposition was dependent on the oxygen partial pressure and total pressure. A high pressure led to the formation of film with large grain size and good crystal quality. So an old film deposited with RF power were generally better than the film with DC disposition. It is believed that with a good conduction control or processing correction, such as the total and oxygen partial pressure, type of plasmaization, bias voltage target to substrate distance, and doping thin film with optimized microstructure and high conductivity could be obtained. That's all from us. Thank you.